So I'm Arthur, and I will be explaining to you about Lagrangian mechanics. So the Lagrangian reformulation of mechanics generalizes Newton's laws and allows for more applications. So unlike Newtonian mechanics, where you're dealing with forces, Lagrangian deals with energy, which is a scalar, unlike force, which is a vector, which is one main advantage. Another advantage of this is that constraining forces do not have to be accounted for when you choose your coordinates, which allow for the constraint rather than having a force. So, firstly, the Lagrangian is defined by the kinetic energy minus the potential energy. So using the calculus of variations, the Euler-Lagrange equations are formulated, and these are partial L with Qn, where Q are your coordinates. There can be n amount of coordinates depending on your system, is equal to the derivative with time of partial L with Q dot. So, unfortunately, one disadvantage of Lagrangian mechanics is that the Euler-Lagrange equations must be modified to account for non-conservative forces such as friction. So one simple example of how to use these is a mass on a spring. So the first step is to define a coordinate system. Here we choose the motion of a mass, which will only be in this direction, to be x. So there is only one Euler-Lagrange equation because there is one for each coordinate. So here the coordinate will be x. So Q becomes x and Q dot becomes x dot, where the dot is just a time derivative. So for a spring, the kinetic energy will just be half mv squared. And because it only moves along the x direction, it will just be L half mx dot squared. And the potential energy is purely stored in the spring, which is just minus half kx squared. Now we put the Lagrangian into the Euler-Lagrange equations to get our equations of motion. So, taking the partial derivative with respect to x of this term, keeping in mind that all coordinates are purely a function of time. So, taking the partial derivative of x, this term is independent, so we only get this. And differentiating that, we simply get negative kx. Now we have the time derivative of the derivative of a Lagrangian with the coordinate x dot. So that is simply just x dot from differentiating this term. Now applying this differential to the x dot there, we get minus kx equals to m x double dot. This is the equivalent of using Newtonian mechanics, where if you draw a free body diagram, you have your mass here, and the only force is due to the spring, which is minus kx. And in Newtonian mechanics, you get that the sum of the forces is equal to ma, which in this case will also just be mx double dot. So both of these formulations will get you the same result, which is that mx double dot is equal to negative kx.